Hello dear friends, welcome to a lecture on ring theory. Today in this lecture we shall study what is known as quotient ring. Quotient ring, or it's also known as a factor ring or ring of residue classes. First we have to consider an ideal U of a ring R. We have studied ideal in our earlier lecture. We should see the definition of ideal of a ring, and with the help of ideal of a ring, a quotient ring is formed. Now the concept is similar to that of quotient group. In group theory we have studied quotient groups, and there we have used normal subgroup to form a quotient group. That means if a G is a group and N is normal subgroup of G, then a quotient group denoted by G by N is the set of all right cosets. Because it is normal, right coset and left coset will be equal Ng or Na, and here we denote Ng, G belongs to G. So this is the set of right cosets for quotient group. And similar to that, here what we shall consider is, instead of normal subgroup, we shall consider the ideal of a ring. And we have defined earlier ideal that U is subset of ring R, non-empty subset of ring R, and U forms a group, abelian group under addition. And further, if R belongs to R, U belongs to U, then this implies both RU and UR are in U. So this is the condition for ideal, and U is ideal. So with the help of ideal we have to form a quotient group, and then we shall form a set R by, denoted by R by U, with the set of all distinct cosets of U in R with respect to addition. See, R by U is the coset A plus U, set of all cosets of the form A plus U, where A belongs to R, and this is actually a ring with addition and multiplication defined on it, and that ring is known as quotient ring. Quotient ring or factor ring, or also known as ring of residue classes of R modulo U. So here actually what we shall first consider is, or we shall prove this forms a ring. First we shall show that this is a ring. This set together with addition and multiplication in R by U defined like this. These are defined. So addition is defined as for two elements in R by U are taken as A plus U and another as B plus U. A in R, B is also in R, and their addition A plus U plus B plus U is equal to A plus B plus U. That is, in this way the addition is defined, and we will show this is well defined. And similarly multiplication defined, A plus U into B plus U is equal to AB plus U. AB is usual multiplication in ring. R is a ring with this addition and this multiplication operation. Now we shall prove this forms a ring. That means first we have to prove that. So actually this is a claim. Now we will be proving this forms to prove R by U forms a ring. To prove R by U is a ring. Now the proof can be considered as, first thing is, addition and multiplication are well defined in R by U. Well defined in R by U, and these are defined here actually, but what is the meaning of well defined? See, what we should have to consider is, let A plus U is equal to A prime plus U, and B plus U is equal to B prime or B dash plus U. Then if these two elements are respectively equal, then their sum on the left side must be equal to the sum of the right side. Then we have to prove that. Then we shall prove a plus u plus b plus u. This addition is equal to a dash plus u plus b dash plus u, because these are corresponding are equal, and if we can prove this, then we say that this addition is well defined. So these operations must be first checked whether they are well defined or not, and if after checking this addition is well defined, multiplication is well defined, we will check the axioms of ring structure. And now that is we shall prove this. Means what is by definition, this is a plus b plus u, and this according to this definition will be a dash plus b dash plus u. This is to be checked, and we shall suppose this as 1. Now what we have is a plus u is equal to a dash plus u. We have a plus u is equal to a dash plus u, and b plus u is equal to b dash plus u. So therefore we can write a as a is equal to a dash plus some element of u, that we shall write as u1. So this is the element a can be expressed in this form, a dash plus an element in u, and here b also we can express as, and b is equal to b dash plus some element of u, that is we write as u2, where u1 u2 belongs to u. And with this expression for a and b, now we shall compute what is a plus b. Now a plus b will be, see, this is the expression for a dash plus u1, and b is b dash plus u2, and this can be written as a dash plus b dash plus u1 plus u2. But you see, u1 and u2 are elements of u, and by closure property it is an element of u, because u is ideal, it is additive group, subgroup of R, and therefore this is an element of u, and we shall denote this as a dash plus b dash plus some element u3, where u3 is equal to u1 plus u2, and that is an element in u. And thus we have a plus b is equal to a dash plus b dash plus u3, and now in 1, therefore what will be a plus b plus u, a plus b plus u is equal to, now we can add u on both sides, and this will be a dash plus b dash plus, or I shall write this in bracket, plus u3 plus u. See, we have added u on either side, and but u3 plus u is again u, because u3 is an element of u. By closure property, this is u, and therefore we have a plus b plus u is equal to a dash plus b dash plus u, and this proves first. So hence 1 holds, therefore 1 holds, and thus we have proved that addition is well defined. So hence 1 holds. Hence 1 holds and addition is well defined. Now next we shall check for multiplication. So this is what we have checked is for addition. Now second, we shall prove multiplication is well defined. That means we shall prove a plus u into b plus u is equal to a dash. See, a plus u, we have a dash plus u. For multiplication to be well defined, the product of these two is equal to the product on the elements which are equal to the corresponding elements, b dash plus u. This is to be proved, and that is what is to be proved according to this definition: a plus u into b plus u. This is product of a and b plus u. For addition, this is addition of a and b plus u. So you note these definitions, and with the help of these definitions we have to prove these are well defined, and thus that means this is ab plus u is equal to a dash b dash plus u. So this is what we have to prove, and now we shall use the same expression for a and b. See, we have what we have is a is equal to a dash plus u, b is equal to b dash plus u, and therefore we have ab is equal to, now ab is equal to, because our earlier supposition is a plus u is equal to a dash plus u. The same thing we are considering here, and therefore we shall consider the same expression for a and b. A dash plus u 1 and b is b dash plus u 2. Now this product with usual multiplication can be written as a dash b dash plus a dash u2 plus u1 b dash plus u1 u2. And now you see, a dash is an element in R. Now see, we have supposed as a plus u is equal to a dash plus u. Here a, b are in R, a dash, b dash are also in R, and therefore a dash is an element of R, u2 is an element of u. See, and therefore here we have as a dash, b dash are also elements in R, and therefore because u is an ideal, we know the product of an element of R and an element of ideal is again in the ideal. So therefore this is element of R, the element of ideal, element of ideal, element of R, and here both are element of ideal. So therefore each element of these each element belong to u. So therefore we can write like this, since u is an ideal, this a dash u2 plus u1 b dash plus u1 u2 is an element of u, and let us suppose that element is equal to u4, and that is an element of u, and thus we denote this by u4, and therefore ab is equal to a dash b dash plus u4. u4 belongs to u, and now we shall add u on both sides and of this equation. So therefore ab plus u is equal to a dash b dash plus u4 plus u. But you see, u4 plus u4 is an element of u, and therefore by closure property this is also an element of u, and this belongs to u. So thus this can be written as ab plus u is equal to a dash b dash plus u, since u4 plus u belongs to u, or is actually it is equal to u, and this shows that second holds, ab plus u is equal to a dash b dash plus u, and therefore 2 holds, thus 2 holds, and multiplication is well defined. Thus we have defined the operation of addition and multiplication in this set R by U, and with the help of this operation we shall now prove it is a ring. the second holds, and multiplication is well defined. Thus both are well defined, addition and multiplication. Next is to show this is a ring. So we shall now show R by U is abelian group under this addition. And these axioms are easy to check. All the 8 axioms of ring structure can be now checked. Next is R by U with addition operation is an abelian group. And what are the necessary properties or axioms of abelian group? Closure. And now you see, closure is easily verified. Two elements of R by U are A plus U plus B plus U, and their addition is A plus B plus U. As A, B are in R, A plus B is also an element in R, and therefore an element in R plus U is an element of R by U, and therefore the closure property is satisfied. Similarly, the addition is commutative, that is easily checked. If you interchange the elements here, B plus U plus A plus U, that will be B plus A and plus U, and because here addition in R, these are the elements in R, addition in R is commutative and by definition of ring, and therefore here this addition is also, addition in R by U is also commutative, and likewise it is associative. If you consider the third element A plus U, B plus U, C plus U, then the addition of A, B and C is associative, and therefore the associative property can also be checked and can be written. You may please write these yourself, and I shall write only directly. We see that the closure property R by U is closed, associative and commutative. Under addition can be easily written or can be easily verified. Now what next is two more, that is zero element and additive inverse. Further, now zero element, we have 0 belongs to R and 0 plus U is an element in, 0 is in R, 0 plus U is an element in R by U, and that is this is 0 element of R by U, and we have, see, this can be checked, we have A plus U plus 0 plus U is equal to A plus 0 plus U, or which is A plus U, and thus 0 plus U or U itself is an element of R, 0 element of R by U, and therefore 0 plus U is equal to U is the 0 element, 0 element of R by U. Now additive inverse, for A plus U belongs to R by U, we have A belongs to R and we have also negative A belongs to R. See, we have negative A plus U belongs to R by U, and these are additive inverses of each other because their sum will be 0 plus U, and by definition of addition, and therefore this is additive inverse of, is the additive inverse or the inverse with respect to addition. So these are additive inverses of each other, and thus this proves R by U with respect to addition operation is an abelian group. Now the remaining properties of multiplication. Now multiplication is closed, that is verified from this. Next, multiplication in R by U. Is closed because A plus B is an element in R. A is an element in R, B is an element in R, A into B is an element in R, and therefore AB plus U is an element in R by U, and therefore multiplication is closed. Multiplication is associative, it can be easily checked. So let further. For that purpose, we may consider three elements as x is equal to, suppose, A plus U, y is equal to B plus U, and z is equal to C plus U, where all these belongs to R by U. Three elements are in R by U, where A, B, C belongs to R. And now for associative property, what we need to prove is x y into z is equal to x in bracket y into z. So what is x y into z? X into y. See, the product of these two, and I shall write directly. The product of these two, here it is defined, and therefore it is AB plus U into z. Z is C plus U. And again the product of these two. How the product is defined? These elements are multiplied, AB and C. So therefore this product will be AB into C plus U. And because this is the multiplication in ring and multiplication in ring R, these are the elements of R, is associative. And therefore we can write this as A into BC plus U. And that can be written as A plus U in another bracket BC plus U. See, A and this product is here according to this. And now what is this? This element is, again, this is x, and BC plus U will be the product of y and z. So, and that is in bracket. And this proves multiplication is associative. Therefore, multiplication is associative. Now the last properties are multiplication is distributive over addition. Next, distributive laws. We shall consider the same x, y, z. So I shall write here distributive laws. This is y, we have considered B plus U, z we have considered C plus U. And for distributive laws, we shall verify the left distributive law, that is x into y plus z, and this we shall prove xy plus xz. So what is x? X is A plus U, and what is y plus z? Y plus z is see, B plus U is y plus C plus U is z, and this is again A plus U, and B plus U plus C plus U can be written as, by definition of addition, that is BC plus U, and by definition of product, this will be A into BC plus U, A into BC plus U, this definition. So we are only using the definition for addition and multiplication in R by U. And further, this can be written as AB, see, this is A into B into C. So we want to show this is a plus u, and finally we want to show this is x into y plus x into z, and x into y, that is x is a plus u and y is b plus u, and that is, see, one thing is we have made a mistake here. It is addition, and therefore this is not b c but b plus c. There is addition of a and b here, it is addition of b and c. So this must be b plus c plus u, and therefore this is actually a into b plus c. Now it is a into b plus c plus u, and because the distributive law hold in ring, so this can be written as ab plus ac and then plus u, and now this is to be written as ab plus u plus ac plus u. These are separated. And what is ab plus u? That is the multiplication of x and y. And what is ac plus u? That is multiplication of x and z. Hence the left distributive law holds. Left distributive law holds. Similarly, the right distributive law can be proved. Right distributive law holds, and thus this all the 8 axioms of ring structure are verified for this set R by U with the addition and multiplication operation defined like this. Hence R by U forms a ring. R by U is a ring. With multiplication and addition and multiplication defined, specially defined. It's not usual, but with this addition and multiplication for cosets, distinct cosets. So this is a ring, and this ring is known as quotient ring. So here actually directly stating the definition of quotient ring, first we have proved it forms a ring structure, and then we are now consider it is a quotient ring. Is a ring known as quotient ring. So why it is known as quotient ring? Now we shall consider example of quotient ring, then it will be more clear to us, because it is known as factor ring, because it this quotient ring divides the original ring in parts. It may divides ring in parts, or it factors ring, and therefore it is known as quotient ring or factor ring. Now example we shall consider as example of quotient ring. We will consider a ring of all integers, and let us denote it by z, may be denoted by z or r. We will denote it by z. Let z be the ring of all integers with usual addition and multiplication. And we will consider an ideal of this. A ring is to be considered and ideal is to be considered, and then we have to form a quotient ring R by ideal. So let 3z we shall consider, 3z, or z is a ring of all integers, means the elements of z are, and we shall write all integers, positive, negative integers also. If 0 is here, then we write positive integers on right of 0 and negative integers on left of 0. So this is z, and further let 3z is equal to 3 into z, small z belongs to z. That means integer multiple of 3 we have to consider, and therefore 3z will actually be every element of this z are multiplied by 3, and thus we will get this as minus 3 into 3 minus 9 minus 6 minus 3 0 3 6 9 etc. So this is 3z, and we know that this 3z is an ideal of z. Earlier we have seen ideal of ring and their example. There we have considered integers and fifth multiple of an integer. So here we have considered 3. Any multiple can be considered, not necessarily 3. We may consider 3, 2, 5, 7, etc. Here 3 is a multiple we have considered, fixed integer we have considered. So this then 3z, it can be checked easily. See, this is a subset of z, and this 3z is additive group under addition. And again, if any element in 3z and an element in z are multiplied, we will get an element in 3z. Second condition of ideal. So 3z is an ideal of z. And now what is the quotient ring then? Then the quotient ring will be, see, r by u. R here is z. Then z by 3z is a quotient ring. And that is the set of set of cosets of z 3z in z, and or residue classes. Now what will be these classes will be, see, we know when from number theory, when an integer is divided by 3, the possibilities for the residues or remainders are either 0 or 1 or 2. These are the only 3 possibilities when we divide an integer by 3, and therefore corresponding to these residues there will be 3 cosets: 0 plus 3z, 1 plus 3z, and 2 plus 3z. So, and z by 3z is equal to, see, 0 plus u, that is a plus u. A here will be 0, 1, 2. Residue, remainder after division by 3, on division by 3. On division by 3, and therefore a plus u will be, that is 0 plus 3z, u is 3z, 1 plus 3z, and 2 plus 3z. Why? Here there is no restriction on a. A is any element in R, and here we are considered only 3. There are infinitely elements in Z. So why this is so? Because if you consider next element, say suppose again 3, then that will be equivalent to this class, because what is 0 plus 3z, here it is 3z. So we will see what is 0 plus 3z. Now I shall write here. See, 0 plus 3z. Zero plus 3z will be again 3z. Same. because each element in each element we are adding 0 and there is no change 3z. And what is 1 plus 3z? 1 plus 3z, you see we are adding 1, then that will be the set 3z, that means minus 9 minus 6 minus 3 etc. 0 3 6 9 and so on, multiples of 3. Here this will be equal to, we will add 1 to this, so minus 8 minus 5 minus 2 1, then 4, then 7 10 etc. And these are the integers which leave remainder 1 when divided by 3, that is 1 plus 3z. And what about 2 plus 3z? Those integers which leave remainder 2 when divided by 3, and this can be obtained by adding 2 in this, so or 1 in this, that is minus 7 minus 4 minus 1 2 5, then 8 11 and so on. You see every element in this coset leaves remainder 2 when divided by 3. So thus the entire ring of integers is divided in 3 parts, and this is the division of ring, whole ring Z. Whole ring Z is divided in all multiples of 3, the integers which leave remainder 1 when divided by 3, and the integers which leave remainder 2 when divided by 3, and thus the whole set of integer has partitioned in 3 parts or 3 factors as this, and therefore this is known as factor ring or factoring. Remaining part we shall continue in our next lecture. Thank you for watching this lecture.